All right, let's get you ready for this. We are diving deep into Chapter 8 from Hines, all about these so-called exotic forces that act on aerosol particles. Now, these are absolutely key if you want to really get a handle on aerosol technology. See, in our big, everyday world, they don't seem like much, but when you zoom way down to the microscopic scale, oh, they run the whole show. Our goal here is to make sure you can explain and defend every single concept on these slides, from the basic ideas to how they're used in the real world. Let's get started. So this is the classic observation, the one that kicks this whole topic off. You've probably even seen this yourself. You take a hot rod or a heating element and stick it in a smoky room, and you see this perfectly clear layer right around it. It's weird, right? The particles aren't just kind of drifting away. They are being actively shoved. The big question is, what's doing the shoving? It's not the air moving around, and it's not static electricity. Figuring this out is the key to understanding the main force we're about to talk about. And here it is. This is the fundamental idea you've got to nail. The whole thing is driven by a force that's created by a gradient in the air around the particle. In this case, a temperature gradient. For you and me, for a baseball, for anything big, these forces are so weak they're basically zero. But for a tiny little aerosol particle, we're talking sub-micron here. These forces are powerful, they're predictable, and they are everything. Getting that distinction is a huge part of the story. So here's our game plan. First, we're going to solve that dust-free mystery, and that's going to lead us straight into our main topic, thermophoresis. Then we'll look at how we actually put that force to work in some really important equipment. After that, we'll zoom out and look at the whole family of these forces, which will show you've got a really comprehensive grasp of this. And finally, we'll pull it all together so you feel totally confident with this material. Okay, let's get to the heart of it. That force creating the clear layer around a hot object, it has a name: thermophoresis. If anyone ever asks you about the less obvious ways particles get moved around, this needs to be the first thing out of your mouth. It's your best, most solid example. This is the definition you need to have down cold. Thermophoresis is just particle movement that's kicked off by a temperature difference in the gas. And here is the one unbreakable rule. The force always points down the temperature gradient. To put it simply, particles always get pushed from hot to cold. That's it, no exceptions. Okay, now here's where we get a little more sophisticated. The why behind this force actually changes depending on how big the particle is compared to the mean free path of the gas molecules. For the really tiny particles, we're talking is smaller than that mean free path, it's pretty straightforward. Imagine the particle. On its hot side, the gas molecules are zipping around, they're fast, and they slam into it with more momentum. On the cold side, the molecules are slower, so they hit with less of a punch. The result? A net push from hot to cold. But for bigger particles, it's more complex. It's caused by something called thermal creep, basically a tiny gas flow that happens right along the particle's surface because of that temperature difference. Knowing this difference is what separates a good answer from a great one. And here's a really cool detail about those tiny particles. The speed they move at doesn't actually depend on their size or what they're made of. Not at all. It only depends on the gas itself and how steep that temperature gradient is. I mean, that's kind of wild and a bit counterintuitive, right? It's a great little detail to bring up to show you really get the physics here. But as soon as we start looking at the bigger particles, suddenly what they're made of starts to matter a lot. Their speed now depends on the ratio of the particle's thermal conductivity to the gas's thermal conductivity. And that's because the particle is now big enough to actually affect the temperature field in the air right around it. And this chart right here, it shows you exactly what I'm talking about. You take two different particles, put them in the same temperature gradient. A sodium chloride particle, table salt, which conducts heat pretty well, moves way faster than a droplet of paraffin oil, which is basically an insulator. The particle's ability to conduct heat changes the game entirely. So for big particles, the bottom line is what it's made of really matters. Okay, so you've nailed the theory. What's next? You gotta show you understand how we actually use it. And the classic, most important application of thermophoresis is a device called the thermal precipitator. So why do we even bother with a device like this? Well, this table tells the whole story. Just look at the numbers. Especially in that sub-micron range, the speed from thermophoresis, even a pretty modest one, it's orders of magnitude stronger than the speed from gravity. I mean, it's not even a fair fight. For these tiny particles, gravity is basically a rounding error. This huge difference is the whole reason the technology works so well. And because this force is so dominant, so predictable for small particles, engineers built a device specifically to take advantage of it. The thermal precipitator uses a very controlled temperature gradient to collect particles with an efficiency that's just incredible. The way it works is just beautifully simple. You've got your aerosol flowing through a little channel. Inside, there's a hot element, usually a wire. This creates a really strong temperature gradient. That thermophoretic force then just reliably pushes the particles off their path straight towards a nice cool surface where they get collected. And what comes out the other end? Super clean, pretty much particle-free air. So, what are the key things to remember here? First, its efficiency is nearly 100% for particles all the way down into the nanometer range. That makes it a gold standard for sampling. Second, it's perfect for collecting samples you want to look at under a microscope. And third, and this is a great point to make, the same idea is used in reverse. In semiconductor manufacturing, they keep sensitive surfaces just a little bit warm to create a thermophoretic force field that literally repels any contaminating dust particles. How cool is that? Awesome. You have totally mastered thermophoresis. But to really show you're an expert, we need to show that you know it's part of a bigger family of forces. They're all driven by gradients, just not always temperature gradients. Let's talk about forces from light. Now, there are two of them, and you absolutely have to know the difference. First, you've got photophoresis. This is an indirect force. The particle absorbs light, but it does it unevenly, which creates a temperature gradient inside the particle itself. That internal heat difference then causes thermophoresis in the gas around it, so the particle basically creates its own force. Compare that to radiation pressure. This is a direct push. It's the literal momentum of photons, of light itself, slamming into the particle and pushing it. The key difference? Photophoresis needs gas to work. Radiation pressure works just fine in a vacuum. And if you want the absolute coolest, most epic example of radiation pressure, look no further than a comet's tail. You know how a comet's dust tail always points away from the sun, no matter which way the comet is moving? That's not an accident. It's being physically pushed away by the constant, steady pressure of sunlight. It is a perfect, massive-scale example of this tiny force at work. Okay, next up, diffusophoresis. What if, instead of a heat gradient, you have a stuff gradient? Imagine you have two different gases mixing together. If one gas has heavier molecules than the other, a particle caught in that mixing zone is going to get hit harder by the heavy molecules on one side. That creates a net force that pushes the particle along. And finally, there's Stefan flow. Now, be careful with this one. It's a little different. It's not really a force acting on the particle itself. It's actually a tiny little wind, a bulk flow of gas that gets created when a liquid is evaporating or a vapor is condensing. And this little wind just drags any aerosol particles along for the ride. It's what causes that clean, dust-free layer you can see around an evaporating drop of water. And you guessed it, just like thermophoresis, we figured out how to use this effect in a big way. In things like Venturi scrubbers, they mix hot, dirty gas with a cool water spray. Water vapor starts condensing onto those little droplets, and that creates a Stefan flow, a conveyor belt, really, that pulls all the tiny pollution particles out of the air and onto the droplets where they can be collected. Okay, let's bring this all together. To really show you've mastered this, you need to be able to connect all these different things into one big idea, the power of environmental gradients. So here are the big takeaways. First, the world of tiny particles is ruled by forces from gradients, temperature, light, concentration, that we just don't notice at our scale. Second, thermophoresis, that simple hot-to-cold push, is a super powerful tool that we use for everything from scientific sampling to protecting microchips. And third, really understanding this whole family of forces is fundamental to the field. It explains how industrial cleaners work and why comet tails look the way they do. And that leaves us with a pretty powerful final thought. We've seen how a simple temperature difference gives us almost perfect control over microscopic particles. So the really exciting question for the future is, what other gradients could we use? What about electromagnetic fields, or chemical gradients, or even sound waves? What kind of incredible control could we achieve if we learned to master those forces too? Think of the new materials, new medicines, and new nanotechnologies we could build. That's why this stuff matters. You should be in great shape to tackle these concepts now.